All right, y'all. Welcome. It's always good to double, triple check things. So yes, our exam is next Thursday, 4 to 6:50 p.m., which means this is our last Tuesday together. Oh, I know. It's devastating not having to show up into this room from 4:30 to 5:50. My heart will also be broken when I get to go home after high school. No, I've enjoyed my time with you all, but I'm certainly looking forward to Tuesdays and Thursdays free, as it should be. It should be exciting to be done with work and all that kind of jazz. So, towards that end, exams there. Today, we are going to go over, I made this PowerPoint, told you I would. It's an overview. It's in the final exam folder here. I'll do some writing on it here and there. I'm pretty pleased with this. We'll see what you all think. I'm glad we get to have this time to do this because so often courses kind of just run right into exams. You're kind of learning content up until the last day. So I'm glad we have this week to, one, kind of there's a little bit of time for y'all to, decent amount of time for y'all to kind of brush up on things, not feel like you have to learn a bunch of new things. You can kind of prioritize your time to the topics that you had challenges with or want to brush up on. But as an instructor, I'm excited to be able to kind of do an overview through all the things that we learned. So today, not really much math. Yes, I'll show the equations, but it's going to be a lot of, here are the concepts we learned every single week. Here's a summary of the entire course. And I'm glad to have this PowerPoint because I think this will also be useful if I do teach this course in the future, which who knows if I will. I've gotten a couple of questions about that. Will I be teaching in the fall or whatever? That is a who knows situation. Adjuncting is a case like you find out when you find out kind of thing. So I don't know what classes they need adjuncts for in the fall. So we'll see. We'll see if I'm teaching this or whatever. We'll see what's available in the fall. I'll still be teaching high school, so it's whatever fits within that schedule. But I'm excited to have this PowerPoint as a thing to just have. So when students look at the course, they can say, hey, here's everything that will be covered in it. It won't make any sense to them, but at least it's there. And for you all, hopefully this is I have no idea if you all need physics 2 after this in terms of knowledge. For some of you all, you may be able to, after this class is finished, just, if you remember some, great. If you forget everything, great. Like, some of you all, though, will need it for the MCAT. If you're doing the MCAT, a lot of stuff will show up. And this may be a useful resource for you when you, couple years, next year, this summer, who knows when, realize they need to remember a bunch of things they learned in the past. You can kind of go through this and get a quick overview of all the concepts. Who knows? Maybe it'll be useful, maybe not. I will never know unless you send me an email years from now. Yeah? So for the final, I'm roughly taking 4 questions from each week's worth of content. So it's going to be 40 questions, but we've done 11 weeks worth of stuff, so that means some sections are only going to have 3 questions. But you can guarantee there'll be 4 questions from each for optics, since this is the last stuff. So 4 questions for optics, 4 questions for the electromagnetic spectrum is what you'll expect. Definitely added things in series instead of parallel. The consequence of this is I just gave a blanket extra 2.5 points to everyone for the free response on that. And the off chance that I accidentally marked yours, the grader marked it incorrectly based on the solutions I provided. So basically 3 points won't change your grade that much, but I did identify that thanks to a student. So there you go. There's that. No discussion section this week. I sent out a survey. If you haven't responded to that, please do. If there's anything you want me to cover on Thursday. I think that's basically... 2 more things. I sent out an announcement. There's a survey that someone at UCF requested that I send out regarding basically the benefits, student perspectives and student experiences in courses with low-cost options. So in our class, something I tried to do intentionally was make it as cheap as possible. Obviously, I can't change UCF tuition. That's outside my control. But textbook and online stuff. So even with choosing the clickers, I hunted around, and that was kind of the cheapest option that provided everything I needed. So the survey is basically asking your all's experiences with that, good, bad, different, and the hope is with that kind of information that maybe more instructors would do low-cost solutions because, I don't know. At least for physics, the textbook generally isn't used. Towards that end, I sent out an announcement that if you do that, I will give you, she will send, the people doing the research will send me a list of the student IDs that did it. And my incentive for you all doing it is I'll give you 10 bonus points in the discussion section. So basically it's worth a discussion grade. Also lets me give points in discussion sections, which you know my feelings about. So do it or don't, up to you. It's not going to hurt your grade. They said they'll take 10 minutes. The details are all there. Don't feel pressured to do it by any means. I mean, it's research, it's optional. But I did want to incentivize it because I like what they're doing. Another thing is the student perception of instructor has probably opened at this point. I remember being a student. I remember just clicking through the things so I could look at my grades. But I really would appreciate your all's feedback there. It's anonymous. If you didn't know, student perception of instructor is completely anonymous. I won't get any of those details until after grades are posted. So it's not going to affect your grade in any way. I'm not going to give bonus points for that because that gets a little conflict of interest-y. But I would love that feedback from you all, especially those. You generally get the feedback from the people that love you and the people that hate you. I would love the middle ground. That's the hardest people to get feedback from anything. So, just put that out there. I'll send out an announcement, try to remind you all. Spend a few moments. I would appreciate it. But you do you. All right, so let's get into it. 2054 overview. Everything we've learned in our quality time together since January. What a journey it's been. So, starting off, and basically the way it's going to work, it's all kind of here. Ideally I'd probably put animations, but I try to keep it concise. First thing we learned about were charges. We came into this class knowing some amount of information, and the first thing we focused on is that charges exist. Just like mass exists, charges exist. And there's only two particles that are responsible for charge: protons and electrons. Protons are positive, electrons are negative, exactly opposite in terms of positive, negative, but the exact same value. Their masses are different. Electrons are 1,000 times lighter in air quotes, 1,000 times less mass than a proton. Anyway, important thing here, these are the things responsible for charge. So anything that has charge is a multiple of 1.6 times 10 to the minus 19. Maybe you have and it's all about what you have extra of, because everything in the universe that is made of matter is made of protons and electrons. Therefore, everything in this room has protons and electrons in it. The question is, do I have extra of one versus the other? Do I have extra electrons? Great. My thing is negative now. Do I have extra protons? Great. My thing is positive now. So, make certain you do remember that. If I say, hey, I have a net charge of 5 coulombs, what do I have extra of and of what type? Or how many do I have extra of? You just take that 5 divided by 1.6 to the minus 19. That's going to give you this whole value. That's going to give you whatever you have extra of. You don't have to do anything extra. So if I said I had 5 coulombs and I wanted to figure out what I had extra of, the net charge would be 5 equals number of protons minus number of electrons. Right off the bat, we know I have extra protons because it's positive. So if I wanted to get how many I had extra of, I would divide those two. 5 divided by 1.6, e to the minus 19. And that comes out to number of extra protons. I don't know what that number is. It doesn't matter. I'm just reminding you all that that's a classic problem. Don't forget that. And the key here is that these are the fundamental charges. All right, great. Opposites repel. That's not right. Opposites attract, and like charges repel. Let's just fix that real quick. So if you have 2 protons, they repel. If you have 2 electrons, they repel. If you have a proton and electron, they attract. Opposites attract. And we had an equation to find the force through that. If things are moving, if things are if they're not moving and then they do move, that's a force. F equals K times Q1, Q2 over R squared. Don't forget the squared. And remember, this is force. Force is a vector, something I should have put here, and I will put it now. These should be absolute value signs because it is a vector. When we're calculating this, we don't care that they're positive or negative. We just put the numbers in. Whenever we do vectors, you just put the numbers in, calculate the force. The direction is based upon opposites attract and like charges repel. And you draw those arrows based in that direction. So that's going to determine whether or not they add or subtract Make sure you kind of look back at those problems and remind yourself how to add vectors visually. Let's just do an easy situation here. If I have two positive charges up here and I put a negative charge down here and I say find the direction of the force, and all of them have the same value because that makes my life easier, makes your life easier. No math required, and I say find the force on this bottom one. Well, let's call this one 1, let's call this one 2, let's call this one 3. The force of 1 on 3 will go that way, up and to the left. Boom, F13. The force of 2 on 3 goes up and to the right. It either points towards or away. That's the only options for when you're looking at two charges. And if you want to add those vectors up, remember, you could just look at this and there's some nice symmetry that makes it easier. But remember, one way you can always add vectors is tip to tail. You draw one of the vectors. This is F2, 3. It doesn't matter which one you draw first. You draw that one, and then you start the next one where that one ended. F1, 3, and your net vector. This is how you can add any vector ever. F net is from the beginning to the very end. Tip to tail. It's a way of visually drawing the addition of vectors, lets you check your work, which is nice as well. So make sure you remember that as well. So there's a week's worth of content in 5 minutes. So we learned about charges. We learned they cause forces on each other, just like mass causes forces on each other. Now, what causes this force? We call that the electric field. The electric field is this made-up thing, just like the gravitational field. You can't see it, but we made it up because we said, I have two charges, one here and one here, no strings attached, and yet they do something. How is that one on the left touching that one? A spooky action at a distance is what we call it. Action at a distance is a distance, something happens. So we said, oh, this positive charge makes a field here. And the value of that electric field, just divide away the other charge from it. So it makes a field which results in a force, and this is actually a good opportunity to show. So, I'll get to that. So there's a field at that point. You put a charge there to experience the force. The direction of that force depends on the sign of the charge, positive, negative. The value of it, of an electric field. An electric field is not a force. It's just a field. You do not get a force until you put something there. Think of a gravitational field. Gravitational fields, there's no force until you have an object with mass that's in that field. The Earth is exerting a gravitational field everywhere in this room, everywhere in all space, forever and ever. Something experiences a force when it has mass and it is in that field. Okay. The unit for this was newtons per coulomb, because the equation for the electric field was just F over Q. F, the unit of F is newtons, the unit for Q is coulombs. So we made up this field, says it's responsible for it. You put a charge here, it's going to experience it, and then we needed to remember the direction. Positive charges move in the direction of E, negative charges move opposite direction of E. We also need to remember that electric fields point away from positives and towards negatives. So in that picture I drew up there, let's call these charges, this one's 1, this one's 2. So this is the electric field due to 1. This is the electric field due to 2. I just picked random spots. It doesn't matter where the field's everywhere. But the field points towards the negative charge and away from the positive charge. So if I picked a random spot, you know what? Let's pick a new spot. Just pick some random spot right here in the middle. Right here in the middle. Red charge is making an electric field to the right. Blue charge is making an electric field also to the right. Let's label those appropriately. It points away from the positive, and the negative charge makes a field pointed towards it. Away from positive, towards negative. And if I put a charge here, let's put two different charges here. So the net field, if you add those two vectors, you get a net field that's pointed all the way super to the right. And if I take that field and I draw that field down here, or just any field, doesn't matter. If I put a positive charge in that field, it's going to move, it's going to experience a force to the right. If I put a negative charge in that field, it's going to experience a force to the left. They're opposites. Basically, you can guarantee whatever a positive charge does, the negative charge is going to want to do the opposite. That's it basically. I can't think of any situation where that's not the case. I guess gravity. But that's because there's no such thing as negative mass. When it comes to electric fields and magnetic fields, whatever a positive charge would do, a negative charge would do the complete opposite of that. So all you have to do is remember one of these. If you can remember what a positive charge does, flip that in your mind, and now you've got what a negative charge does. You only need to remember half the information. Okay, cool. Charges make fields. They affect other charges. Basically, we're just making up a reason why the first step I talked about. No one has ever seen a field. All we have experienced is the force due to this field, and we found it useful to make up a reason for why this force is happening, just like with gravity. We decided to make up a gravitational field to explain why it's happening. Now, there's many ways to make these fields. They all boil down to charges. So you can have point charges, and the electric field is kq over r squared. Still got that square term. But we found that if we put a bunch of fields together, well, yeah, I'll jump back to flux in a second. If I have a line of charge, so a line of charge is exactly what it sounds like. I've got a line with charge on it. If I want to find the field at some distance r away from this here is the charge density. Lambda equals Q over L, charge per unit length. If I want to find the field there, and it'll end up always pointing away from the charge, there you go. That's the equation for it. If I have a plane of charge, the plane is the most important out of these three because it feeds into capacitors. The plane of charge is the most important because if you'll remember, a capacitor is just two of these together. The plane of charge, that's like a piece of paper with a bunch of charge on it. The electric field, still going to point away from it if it's positive charges. It could point towards if it's negative. The electric field has no dependence upon distance. This is true for the plane. This is true for 2 planes of charge. It's true for 3 planes of charge, 10 planes of charge. Who cares? What matters here is that a capacitor is made from 2 of these together. And if one of them doesn't depend upon R, then 2 of them doesn't depend upon R. That was a question on the first test that a lot of people missed, as I said, hey, here's a capacitor. If I measure the electric field at that point, and then I go somewhere closer, how does the electric field compare? It's the exact same value. If I go somewhere else, it's the exact same value. I am denoting that here by drawing all arrows that have the same exact, all those arrows are roughly the same size, as good as I can draw them. I guess I could have copied and pasted them. The electric field is the same everywhere. Whereas for the line of charge, if you get closer, radius is, R is getting bigger, smaller, and therefore the electric field is getting bigger. So for a line of charge, it does vary based on distance. For a sphere of charge, it does vary based on distance. For a plane, it does not. And remember, the rationale is we imagine this plane is infinitely large. It's not, but if you get really close to a wall, it looks infinite because you can't see the sides anymore. All right, sigma here is charge density. It's the charge per area. Charge divided by the area of that plane. All right. Then we have a sphere of charge. You got a sphere. There's 2 equations. If you want to find the electric field inside the sphere, use that. The first one, which is K capital Q, that's the charge of the whole thing. R is the distance to the point. Big R is the radius of the sphere. So that's inside the sphere at some point, little r. If you are outside the sphere, let's draw the exact same picture, but my point now is outside of it. We don't care, and this is kind of interesting, you don't care about the radius of the sphere anymore. As far as we are concerned, when you are outside of the sphere, it looks like a point charge. Looks like an electron, looks like a proton. It acts the exact same way, kq over r squared. Except now it's a big Q because it's a lot of charges, which is kind of interesting. These are approximations that are useful. Turns out when we get really far from things, the complexity goes away. So, all right, there you go. 3 different charge distributions. We've done problems on them, quickly looked through them. It's fairly straightforward stuff. There's not really any complexity here. The only thing of note, I say complexity, it's just math. There's no conceptual fanciness here, with the exception of the plane of charge not depending upon distance. That's the only key kind of thing that you do need to remember. Electric flux we introduced here mainly so that when we saw it in magnetic fields, it was one less concept for our brains to have to wrap around. Electric flux is the electric field times the area times cosine of theta, where theta is the angle between the area vector and the magnetic field. So I'm not going to attempt to give you all one where I'm never going to give you a picture because it's a nightmare to draw. So say I have an electric field going to the right, my area vector is perpendicular to the surface. The angle, when we're talking about angle, it's the angle between the electric field and the area vector. I am only drawing this picture just so that angle can be clarified. That angle is referring to the angle between the area vector and the electric field. Area vector is the vector that is perpendicular to the surface. The tip I had for you all is imagine you take your pencil, put the eraser flat down, bam, you got the area vector. You can apply that to any surface ever, if you ever have to calculate area vector for some reason in your life, outside of this class. Can't imagine why you would. All right, but we do use it. We've used it in this class, so useful now. All right, 2 weeks down. Forces, done. Electric fields are responsible for forces. So one of the things as we're going through this is I want to highlight how everything builds. We had to introduce charges because they exist and they cause forces on each other. These forces we say is due to a field. Wonderful. Well, it turns out we can think of this in another way. Just like we can think of gravity in terms of gravitational fields, we can also think about gravity in terms of energy. We can think about everything in the universe in terms of energy. And a rule of thumb is that every single object in the universe wants to get to a lower potential energy. You can use that to explain anything. It may not just get you where you want to be, but it's true. Every single thing in the universe wants to get to lower energy. So we introduced this idea. All right, great. That means charges. There's some energy associated with it. Let's make this a little bit bigger. So charges gain this energy from being in the field. How do we know they have energy? Energy is the potential for something to do work, for something to experience a force. We already said they have force, so therefore they have energy. Great, woo. The energy is K, if you have 2 charges, K, Q1, Q2 over R. The square term is gone, comes from doing an integral, don't worry about that. And remember the connection that's really going to help you with this is if you understand gravitational potential energy, it's the same idea, the equation is different. K, Q1, Q2 over R. Previously, when y'all learned about gravity, it was mgh. You will not need to know mgh in the final, but if you do the MCAT, you probably won't remember that. We can use this in our conservation energy equation to find the velocity moving charge. I already went ahead and put it in the simple form that I told you all. Basically, all conservation energy problems in this class will just be QV equals 1/2 mv squared. This is coming from the more general conservation of energy was that potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. That's the one that you learned hopefully decently well in your physics 1. If not, whatever, it's not going to come up here. And the way I've set up all the problems, if you rearrange things, you find that the negative change in potential energy equals the positive change in kinetic energy. And at the end of the day, it all boils down to change in potential energy is Q times V. Change in kinetic energy, in our case, will be 1/2 mv squared. Because I will not, the reason that would not be true is if my object was already moving, and then at the end is also still moving, just at a different velocity. Every problem I have given you all, and to prepare you for the final, same thing's going to happen here. It either starts at rest, and at the end is moving, or it starts moving and ends at rest. In that case, one of those kinetic energy terms is 0, because the velocity is 0. So, because the problems I give you involve a particle either going from not moving to moving, or moving to not moving, it boils down to just QV equals 1/2 mv squared, where this V is a difference. Voltage is only a difference, just like height. We talked about height is always a difference. Whenever you are measuring height, you are implicitly, maybe explicitly, but generally implicitly defining a bottom and a top. If I measured how high up I am right now, what's bottom? From where? So maybe we say my feet is the top, but what's the bottom? Is it the floor I'm standing on? Is it the floor down there? Is it the center of the earth? Even height is relative. Even height is a difference. When you're measuring how tall you are, you measure from the top of your head to the bottom of your shoes. There is a difference involved. You know, start point, end point voltages is the exact same way. Whenever we define voltage, it's generally with reference to a zero. So if I say 9 volts, 9 is the high, 0 is the bottom. 9 minus 0. You could touch a 1,000-volt power line and be perfectly fine as long as another part of your body is not touching a 0. If you're all at 1,000, you're fine. It's kind of like if you're at the top of a mountain and it's flat. You're fine. You're not going to fall down the mountain unless there's a lower point. You can only fall if there's a lower point. Voltage only matters when there's a lower point. So pro tip, if you all ever see a downed power line and you happen, like say a power line falls next to you, you are fine as long as the distance between your feet is very small. So you kind of do the little shuffle away. If you make a big step, you've introduced a big potential difference because your foot, 1 foot is closer to the power line, 1 foot's farther away from the power line. Potential difference, maybe the side of your body is a less resistive path than the ground. There you go. Hopefully you never have to use that. I don't know why you would. I've never had to use it, but it's interesting. All right, so conservation of energy, QV equals 1/2 mv squared. So talking about voltage, I've already kind of mentioned voltage, but yeah, it's like height. It is not energy. Voltage is not energy. Just like a field is not a force. A field's not a force, voltage is an energy. But if you put a charge in a voltage, now it has energy. You need to put a charge there for it to get the energy. There could be a voltage, but you get no energy until you put a charge there. So energy is Q times V, which is the charge that's in it, and the V is the voltage it experiences there. We can calculate the voltage of a point charge if we do want to find the voltage some distance away from a point charge. It's KQ over R. And positive charges move the way you expect. They go from a high height to a low height, if we think of voltage like height. So if we draw a little picture somewhere, let's just do it here. If I have 0 volts here, and I have 10 volts here, and I have negative 10 volts here, a positive charge will move the way we expect it to, which is to lower voltage. Makes sense. You're like, it moves to lower. Great. Negative charges, as I've told you all, do the opposite. Negative charges move to a higher voltage. Why? Because that's a lower energy for them. Energy is Q times V. Negative charges are negative. Negative 10 is a smaller number than 0. Negative 10 is a smaller. Why does it become negative? Because the negative charge is negative. Negative times a positive is a negative. So, it all still fits together. But at the end of the day, just remember, positive charges go to lower voltage, negative charges move to higher voltage. Both of them are moving to lower energy. Both of them are moving to lower potential energy. It works out that way with that U equals QV. We can also relate the voltage in the electric field. Technically, this relationship involves an integral, but yay, we don't need calculus in this class. So we can only use the case when the electric field is constant, V equals ED, done. V equals the electric field times the distance. So this is largely just used in a capacitor. The electric field is constant. We still get a voltage because there's a distance between the plates. Multiply those two numbers. Ta-da, the voltage. You get the voltage of the capacitor. All right, so forces due to charges. What causes them? Electric fields. Great. Let's think of it another way. Let's introduce energy. That's voltage. This voltage is another way of explaining why charges move. They want to move to lower energy. Again, still all connected. We're just looking at why charges move in a different way, trying to understand it, explain it, do useful stuff with it. Great, now that we've got voltage, now we know that charges can move. Let's do something useful with it. Let's build devices that are useful. So towards that end, I introduced the idea of resistors because we're starting to get into current and circuits. But before I could start talking about circuits, I need to introduce resistors. Really straightforward. well, resistors and capacitors. I don't know why I lost the word capacitors here. Capacitors and resistors. So we start off with capacitors. I mentioned just in the last slide. I'll make this a little bigger so it's easier to read. Capacitors are just two of those plates. Two of those plates, those parallel plates that have a constant electric field. If one of them has a constant electric field, then two of them have a constant electric field. Move things up because it's a lot of stuff on here. Great. So we introduced the thing of capacitance, which is what it sounds, capacitance. It's this capacity to store charge. We take these parallel plates and we basically think of them like buckets for charge. We can put them in a circuit and they can hold a bunch of charge. They make an electric field inside. We define this unit called by we. Some guy in the past with the last name of Farad came up with this idea, and so he gets the unit named after him. So this has this capacitance, this ability to store charge, units of Farad. When you apply a voltage, you need a voltage to fill up these buckets. You need something to hold those charges on there. They're not going to want to stay, because if you try to put a whole bunch of positive charges in one place, why would they stay? They want to repel off each other. So how do we keep them there? Well, we take a battery, which has got some voltage, and so it's going to kind of make it advantageous for a bunch of positive charges to want to build up here, and it's going to make it advantageous for a bunch of negative charges to build up there. That voltage is kind of introducing a height difference, which then they all pile up in one spot until they no longer want to pile up. We said C equals Q over V, where Q is charge, V is voltage, C is capacitance, and the energy stored in the capacitor. This is where you have to be careful. Previously, for 2-point charges, energy was Q times V. Now it's 1/2 Q times V. Comes from the math, comes from the derivation, shock and all, comes from calculus. A lot of things come. There's a reason engineers have to take calculus. A lot of physics derivations require it. It's a tool. Calculus is just a tool, just like algebra is. So energy equals 1/2 QV equals 1/2 CV squared equals 1/2 Q squared C. All of these, they start with 1/2 QV, and then you just use that C equals Q over V to get the other ones. What you all do need to remember for sure, so great, capacitors exist. They store charge. Couple main things. One, capacitance, at the end of the day, only depends upon geometric qualities. Capacitance only depends upon geometric qualities, meaning the area of the plates, the distance between the plates, technically what's made of, because there's that cap in front of it, but again, that's not going to show up. Don't worry about it. So how much charge this can store only depends on, and I'm going to use this word loosely, shape. I don't even want to use the word shape. I'm going to use the word geometry, but that's not even exact wording I want to use. Basically, how it's formed. What's the area of the plates? What's the distance between the plates? Measurable things you can measure with a ruler. How it's designed. It does not matter the voltage of the battery. It does not matter how much charge is on it. If you buy a 1 farad capacitor from China, because everything comes from China now, if you buy 1 farad capacitor from China and it arrives to you, it's going to still have 1 farad. Why? Because it's got a set area, it's got a set distance between the plates. It's based on how it's built. Maybe maybe I can put that set. Only depends on the geometry. So that kind of leads us into, so we need to remember that, and then we need to conceptually remember what stays constant when. There's 3 variables: voltage, capacitance, and charge. So capacitance I already explained. Based on geometric, if you do not change the area and you do not change the distance between those plates, capacitance is the same. Who cares what it's connected to? As long as you don't blow up your capacitor. If I buy a capacitor from China, and then I throw it, or I give it to a friend, and then they drive to Michigan, and they connect it to a different battery, and they give it, who cares what happens to it? If I'm not changing the area of the distance between plates, capacitance is a constant. Voltage is constant when it's connected to the same battery. The battery is what's defining the voltage on the capacitor. It has 0 voltage when it's not connected to a circuit. The second you connect it to a battery, bam, it gets that voltage, assuming it's the only thing in it. If I change the area, if I change the distance, if I change the capacitor itself, who cares? The voltage is not defined by its capacitance. The voltage is defined by what it's connected to. Charge is constant. When it's charged, disconnected from a circuit and never discharged. I mean, think of it like a bucket. The amount of water in a bucket is defined by how much water is in the bucket. You fill the bucket with water. If I pour that bucket into another, well, that's not great. If I have that bucket, the only way I lose water is if I pour some out. That's what it comes down to. Charge is constant as long as I don't discharge it. And that's with the caveat that it's disconnected from the circuit. Again, think of filling up a bucket. If it's in the circuit, and I'm currently, I have like a hose connected to it, and I filled it up with water. Yeah, if I turn that hose to a higher pressure, I'm going to put more water in my bucket. But if I disconnect it from it, who cares what I do with the hose? It's no longer putting water in the bucket anymore. If you charge it and don't discharge it, it's the same charge. It makes sense. Hopefully. Capacitance, based on what it looks like, what it's made of, the geometry, voltage, as long as it's connected to the same battery, charge, as long as you're charged and not discharged, and disconnected from the circuit. That's key. That's key. You have to, every word I put here is important. And this should ideally be on your first note card as well. If you're afraid you'll forget it should be on your first note card. You can go back and check it. If not, add it to your thing. All right. Great. Capacitors. Done. Resistors, much simpler. Look how short that is. Resistors do exactly, thankfully the words kind of match the English words. Resistors resist. What do they resist? The flow of electrons. Higher the resistance, the more they resist it. Named after the guy who found them, Ohms. I think his last name was Ohms. It was something very similar to Ohms. If not that, we use the capital Greek letter omega. Symbol is R in the equation. Resistance is just like capacitance based on what the material is, what it's made of, and its geometry. Its length, its cross-sectional area, the material it's made of. This row here is resistivity. So if we draw a resistor, bam, you could just imagine it as a tube. This would be the cross-sectional area. So that's its area. Its length is its length. And rho is resistivity. That is too many I's, too many S's. Resistivity. That is based on material. I will give that to you. Or I will say calculate it. One of those two things. It's not something, every material, copper, gold, wood, your human flesh, all of it has different resistivities. How do you calculate those? You don't. You take them to a lab and they measure it because the calculations are, I don't even, be very complicated. It's based on how electrons flow through it. You can imagine that's a very complicated thing to theoretically determine, how electrons would move through a material. So that's just a value based on the material. Every single material's got a different one. Key point here, resistance is purely based on what it's made of. You buy, just like capacitance, if I buy a 100 ohm resistor, that's not going to change if I ship it from China or throw it across the road, as long as I don't break it. And it's pretty hard to break resistors. So, great. Except, almost we're at test one. Almost we're at test one's worth of stuff. So this is last thing, really simple as well. So we talked about capacitors, we talked about resistors. Now we're finally getting to circuits. Okay, so a lot of things we kind of introduced. Talked about charges and fields and voltage. And we introduced this idea of something that could resist the flow. And we introduced the idea of something that could store charge. Put it all together and you build yourself a circuit. Have something with voltage. Have some resistors in it. Have some place for current to flow. Voltage is what makes them flow. Current is the flow. Resistance is what is opposing the flow. Put all that together, you get Ohm's law, V equals IR. Every single electrical circuit has a voltage, a current, and a resistance, assuming it is on. Every single circuit has a resistance to it. Even the thinnest, the fattest wire in the world has some resistance. V equals IR, Ohm's law used it a heck of a lot. And you can get how much energy is used per second by P equals IV. Power M equals I squared R. Look at that. We just derived the second. So the three versions of power are all just coming from V equals I R getting chucked in there. P equals IV equals I squared R equals V squared over R. This is what you are charged for. You are charged for kilowatt hours. I will not test you on any problems with kilowatt hours or anything like that. But I want to mention it just because you do experience this. When you pay your power bill, remember electricity is basically liquid energy. You are paying for the energy used per second times time. When you do that, you are paying for the energy that you used. Power is energy per second, so if you multiply that by time, you just get energy, which is kilowatt hours. Watts, energy per second, hours, time, bam, just get energy. Okay, so test one. Test one was on charges. Moving charts, electric fields, voltage, current, resistance, everything to do with that. We had a little bit extra that we needed to cover with circuits, series and parallel, so those didn't show up on test one, so that's got introduced in test two. But once we cover that, that's basically everything to do with electric fields and voltage, is that first chunk. So, after test one, we started to talk about just a little bit more nuance. If you have a bunch of circuits together, everything up to this point was basically one resistor, one battery. Great, what happens if you have a bunch of them? Well, if you have wires that meet together, what's going to happen to the current? It's going to split. What goes in must come out. A junction is just where more than one wire meets. If I have I1 going in, I2 going out, and I3 going out, the junction rule says I1 equals I2 plus I3. What goes in must come out. Really straightforward problems, really simple, but important conceptually. It's important to recognize current as a flow. Well, yeah, if there's more than one path like a river, the water I started with, if it breaks into two rivers, I didn't get any more water. Hopefully I didn't get any less water. What I start with, I must end with. What goes in must come out. So that's an important idea when it comes to circuits. Then we introduced the idea of series and parallel. So series is when you have one after the other. Key way to identify this, no junction between them. So one after the other. Who cares if they bend? Who cares if the wires bend? So great, let's have one up here and then go down here and then go up here. Who cares what the wire's doing as long as it's not splitting? As long as there's no junction, that wire can do, you know what? Great, let's have one go down here. Who cares? As long as the wire doesn't split, it's in series. Series is one after the other with no junctions between them. Resistors add up nice and easy. Literally you add them. Easy. Capacitors gets a little bit more wonky. 1 over C1 plus 1 over C2 plus blah, blah, blah. Lots of problems to kind of practice with that. Not too much to say there. If you can identify that it's in series, the math is simple. The mistake that I see when doing these problems is just identifying is it in series or parallel. So make certain you're good at doing that. Current is constant in series. That is very important to remember because who cares if the river bends? You still have the same amount of water. If the river takes a left turn, I didn't lose any water. If the river goes through somewhere where it gets thinner, I still have the same amount of water. If it goes wider, I still have the same amount of water flowing. So, current, how much charge is moving through that wire has to be constant. Otherwise, it's building up somewhere. And that could be a concern. But it's not. So, no concerns. Not in this class. So, there you go. Current constant in series. Parallel is a little trickier to define. Unfortunately, the definition I landed on kind of lends itself to what you have to remember. Parallel circuits have the same wires on both sides. When I say same wires, we do not care if that wire splits. We do not care if there's junctions. That wire can split as much as it wants. Bam, splits here, splits here, splits here. Great. This is going to look all crazy. This one splits, this one goes over here, and then they all meet up in some crazy thing over here. The important thing is that all of these have the same wire on this side. There's no resistors in between where they all meet up on one side. There's no resistors where they meet up on the other side. They all kind of share a wire. I can get from one side of the resistor, any one of these resistors I can start on the right side and end up at the right side of another resistor. Any of the resistors I can start on the left side and end up at another left side of a resistor without running into anything. So they have the same voltage because of that. Voltage does not change at junctions. Voltage is like height. If a river splits, that does not mean that the height changed. It just means there's multiple paths for it to go. Voltage does not change at junctions. So, if they have the same voltage on one side, the same voltage at the other side, the difference in those is the same. And remember, whenever we talk about voltage, it's a difference. So voltage is the same in parallel. Resistors get all disgusting. You have to do 1 over R1. 1 over R1 plus 1 over R2 plus 1 over blah, blah, blah. If you want to combine all of these. Remember, whenever we say R net, the idea is we take this gross looking circuit and we change it into, oh, so pretty, one nice resistor. And then you can work backward to do stuff, and we did problems like that. When it comes to R net, it's simplifying the circuit for use in calculations to find various values. Great. Capacitors add nicely in parallel. They do the exact opposite of resistors. Okay, series and parallel. Great. That's the key here. What is a series? Make certain you're confident at identifying a series circuit. Make certain you're confident at identifying a parallel circuit. There was a good problem. Well, good is subjective. On the last test, I made a problem I liked. Maybe you hated it. But it had a lot of good practice as far as identifying series and parallel. So you can go back and look at test 2, look at the solutions, and look at that free response problem. If you're stumped on identifying series and parallel, it's a good practice one for you. And I've worked out and I've identified which one's which. Okay, great. Charges, as far as electric fields and voltage and all that stuff, bam. All that electric field stuff, done. We then entered into magnetic fields, which were mathematically simpler, but involved a bit more kinesthetics, i.e. waving your hand around to find various things. So, magnetic forces. We got electric forces, now we have magnetic forces. Why? Because they exist. I'm sorry, I don't decide these things. You know, at some point, if you all learn enough about this, you'll learn that electric fields and magnetic fields are one and the same, and that's weird, but for now, we treat them as separate things. Magnetic fields cause forces on moving charges. So basically, someone did an experiment. They said, great, charges experience a force when they're near each other. But then they found when they're moving, there was something they couldn't explain. They were doing things that electric fields could not explain. So that means there's something else happening. This magnetic force is happening. Basically, this is how most of physics was. The foundation of physics is observing forces, really. You know, Newton was the dropping an apple. They call him the father of physics because he defined forces. And then everything after that was just identifying what causes these forces, and then we go from there. So, charges cause forces on each other due to electric fields. If they are moving, then they cause forces on each other due to magnetic fields. Unit is Tesla. 1 Tesla is very big. So the unit for the field is Tesla, the unit for force is newtons. We said if you have a charge moving in a magnetic field, so a charge, let's make it positive, and it is moving to the right, and it is in a magnetic field that is pointed, who cares, up and to the right a little bit. The angle between these, we multiply charge times velocity times magnetic field times sine of the angle between them, and that gives us the magnitude, not the direction. The direction was way more fun. We'll get to that in the next slide. I'm sure you remember. Remember, this just tells you the amount. Does not tell you which way it's going to go at all. Just tells you, hey, this is the force on it. Number. Done. If we have a current carrying wire, current is. So let's just draw this exact same problem. Now I've got a whole bunch of positive charges moving, and we define a whole bunch of positive charges moving as current. So these things, there's a current going this way. That's analogous to velocity. Positive charges moving that way. It is velocity. A bunch of positive charges moving that way. you have a magnetic field in some direction. The angle between those two, oh, and we have the length of the wire as well. We got to chuck that in there to account for all the charges. So these two pictures are the same thing. The bottom one's just a heck of a lot of charges. The top one is one charge, but the equations for these are the same. This is just a bunch of charges on the bottom. The top one is one charge. I also like the wire. I more commonly gave you all problems where I said find a force per unit length. Because that is a more useful quality to have than force on a wire. Because at the end of the day, you're not going to measure a super long wire and include that. You will just care about the force per piece of it, and then you can multiply that for yourself if you want. So towards that end, if you divide by L, you get the force per unit length. If you want the force per unit length, just take this L right here, divide it to the other side, bam. Force per unit length. Done. Easy peasy. So let's make that a little bigger, easier to see. So great, there's our forces. They happen. You have a moving charge, it experiences a force. Great. Now we have the joy of finding the direction of the force. And on the next slide is just the whole write-up for right-hand rule number 1, which we've written now quite a few times. Start with a flat hand. Fingers point the opposite of positives. Negatives do the opposites of positives. So let's make up a problem. Positive charge moving to the right. Magnetic field is up. You know, we've done so many of these. These are vectors. So flat hand in the direction of B, palm in the direction of B. Our force is out of the page. Definitely make certain your brain hasn't forgotten how to do these. Plenty of practice ones. Won't take you long to remind yourself, but make certain you do. Make certain you don't forget how to do this, and make certain you do not forget that if a negative charge, the force is in the opposite direction. It's a real bummer to miss that, because you could do all the awesome right-hand stuff and then just forget that tiny little detail and get the problem completely wrong. The downside's a multiple choice. The other thing in this one, a lot of you will miss this question on the test too. I say a lot, about exactly half. I gave a problem, I said a charge enters a magnetic field. A positive charge enters a magnetic field. And that magnetic field, and I don't remember, I'm just going to make it up. I'm going to say it's into the page. I honestly don't remember if it was into the page or out of the page. It was one of those two. I said, what will that positive charge do? What path will it take? And the answer was, as it enters the field, so velocity is to the right, field's into the page. Initially, at this beginning spot, let's make this thing red so it's easier to draw. The red, it will experience a force that is upwards, initially. But as time goes on, that force will cause it to go upwards. But what happens when it's upwards now? At some later point, now it's going up. Fantastic. What's the direction of the force now? Now, velocity is up, hand is into the page. Oh, now the force is to the left. So now it's experiencing a force this way, which means at some point it'll be up here. And the long and short of this is that a charge entering a magnetic field will end up making a circle. In this case, a counterclockwise circle. Make certain you know the difference between counterclockwise and clockwise. Unfortunately, it's the best way we have to describe the direction you're going in a circle. Counterclockwise, opposite direction a circle goes. So, this positive charge would make a circle going counterclockwise, and that introduces our equation here. QVB equals mv squared over r. QVB, we've already seen, that's the force in the charge. mv squared over r comes from your Physics 1 class. If you have something going in a circle, all the forces that are causing that equal mv squared over r. Centripetal force. Simple, I say simple. It's a nice, elegant kind of equation, but it all comes from all the forces equal mv squared over r. But definitely what I want you all to remember is that a charge entering a magnetic field will make a circle. Why? Mainly because it uses a lot of the concepts. At the end of the day, do I really care that you know it makes a circle? What I do care about is that you can identify the force on it. And the thing that's nice about this problem is it makes you realize you can't just think about What it's going to do a little bit after. What about after that? What about after that? What about after that? So I saw a lot of students say this is going to make an arc straight up. That explains the first piece of time, but it won't just keep going straight up. You have to think a little bit further, a little bit further, a little bit further. And so that idea of kind of thinking about the full picture, that's the reason I like this problem. Is you don't just think a little bit ahead, but you keep thinking what's going to happen after that, after that, after that, after that. What's the full picture? What's the single ultimate? And it's just going to make a circle. And forever. It'll get stuck in that circle. And just keep making that circle forever and ever and ever. Assuming the field is uniform everywhere. All right. Okay, moving charges experience a force in a magnetic field. Fantastic. What causes them? All right, let's make up something called a field. Done. Made up. How do we calculate the field? This is going to sound shocking. Calculus. So I didn't tell you. So then I just gave you the equations for the magnetic field due to various situations. Magnetic field due to a straight wire, magnetic field due to an arc of a wire, a loop of wire, and the solenoid. And just like the capacitor, this was a problem that a lot of us missed, basically exactly half. The solenoid is the loop. The solenoid magnetic field does not depend upon distance. Does not. Who cares if you are located here or here or here or here or right in the middle? The field, and let's say you all can see for yourself that the current, if I have the current going in this way, the magnetic field is going to point to the right. Every point in here, the magnetic field is the exact same. Why is this important? Because these are used in circuits. If you want a constant magnetic field, you make a coil. And this is used, they're called inductors. We didn't really get into them too much. But there's three basic elements in every circuit: resistors, capacitors, and inductors. We didn't really worry too much about inductors, but they are a fundamental thing. If you all ever look at a circuit board, you may see something that looks like a coil of wire. It depends on the circuit. You may not always see them, but these are literally just a bunch of wires circled up. If you ever see that, that's a solenoid, and that's why. It makes a constant magnetic field. Great. Shows up in circuits, so that's why I need to emphasize it. That's why I like to emphasize it, because it actually is real. No one's making magnetic fields with straight wires. No one's making magnetic fields with arcs of wires. There is people making magnetic fields with loops of wires. But predominantly it's these solenoids. Alright, straight wire, I'll quickly draw that just to, we've drawn this a bunch of times. You have a wire, some distance R, and some current I. Fairly straightforward. The arc of wire, I'm going to tell you all it's not going to show up. I put it here because I taught it to you, and it leads into the derivation for the loop of wire, but you don't need to worry about it really. R, here's this. If I have a full loop, my angle. So here, theta is the angle of the arc. If that's 2 pi, bam, you got a loop of wire. If you plugged in 2 pi for that, you get this equation. When theta equals 2 pi, you get that equation. Some radius r, some current I. Okay, so here's the different ways. You can make a magnetic field due to any crazy geometry of wire. These are just the ones I gave you because it turns out it's really hard to, if I have a bundle of my wire here and I said find the field, it would, disgusting. I have no idea how to do that. Very complicated. So we have to pick specific, just like when we did the electric fields, you only had a line of charge, a plane of charge, a sphere of charge. When it comes to magnetic fields, you will only have a straight wire, a loop of wire, or a solenoid. I skipped the arc because I'm not going to test you on that. And you do need to remember that a solenoid is the only one that doesn't depend upon distance from the wire. In a certain distance. How closely packed can you get those coils? The radius of that solenoid does not matter at all for the purposes of our class. Reality is it may, but for purposes of our class for this, we assume an infinitely long solenoid, so it doesn't matter. All right. Yay, right-hand rule number 2. How do you find the direction of these fields? All of these equations just gave you the amount. They were vectors. So, to find the direction of field due to a type of wire, you start with your hand flat. Let's go ahead and draw a current going here and say I want to find the field. You know what? Let's make it different. Let's do, we'll do a simple one. Current, some point P. Start with your hand flat. Thumb in the direction of current. Bam. Fingers point towards where you want to find the field. Bam. palm points out of the page, that is the field at point P, out of the page. If I gave you a current carrying wire like this is a current carrying wire going into the page, and I said find the magnetic field here. All right, same thing. Thumb will go into the board because that's the way current's going. Fingers go towards point P, which is to the bottom left. My palm points up and to the left, up and to the left. So this applies to every single situation. Thumb in, palm up and to the left. Oh, is this dead? Hey, it's not dead. Great. The webcam seemed to have turned off. Oh well. All right, if multiple wires, I gave a problem that I liked. Again, ideally I'm not giving you problems I don't like. Whether you like them, sorry, may not be the case. On the test, the last test, I gave a problem that had 4 wires. 2 straight ones. It had a wire here, it had a wire here, it had a loop, and it said find the field here. This problem is just doing this 4 times. Find the magnetic field to wire 1. Let's call this one 1. Find the magnetic field to wire 2. This loop here is 3. This loop here is 4. You break it into pieces. You break this problem into 4 pieces. Pretend like the other pieces don't exist until at the end when you combine them. I highly recommend you all look at this one. It looks worse than it is. I'm just finding the magnetic field at that point due to a straight wire going up. I'm finding the magnetic field at that point due to a straight wire going down. Due to a loop that's going counterclockwise and a loop that's going counterclockwise, whatever directions these may go. And then the only thing that's tricky here is you just need to know whether to add them or subtract them. So in this case, wire 1, the magnetic field is into the page. So B1 is into, B2 is also into. You all can look at this, look at the problem. But that's in the solution. I'm not going to spend the time on it because we don't really have that much time left. All right, so check that one out though. Really good example of how to add up multiple together. If you had 10 of them, you would do the same thing. Adding more of them just adds more work, not necessarily more complexity, just more doing the same thing. All right, Faraday's law. This is the last thing I taught you all. So, moving charges experience a force. Due to what? A field. A magnetic field. All right, great. And we can make this field from wires. So moving charges experience a field, experience a force. Moving charges make that field. Just like gravity. Things with mass make gravitational fields. Things with mass experiences force due to gravitational fields. Things with charge make electric fields. Things with charge experience a force due to electric fields. Blah, blah, blah. Okay, so on and so forth. Faraday's law says, great, what's the use of all this? We can, by having a changing flux, aka, if you have a closed loop, it has to be closed. If there's a break in it, it does jack squat. There has to be a closed loop. If the field lines are changing in that, it actually generates a voltage. This, Faraday's law, is the connection between electric fields and magnetic fields. A changing magnetic field generates an electric field in the wire, which is kind of cool because then we can do stuff with it. This is critical because this is how we generate electricity. We can spin a coil in a magnetic field, it will experiencing a changing number of field lines given by this equation. EMF is just voltage. Remember, voltage comes from electric field, so that's where we're seeing this connection. We have voltage equals a changing magnetic field. This is the one topic, well, I guess like two, where they kind of intersect together. As the field is changing, you get more or less field lines, and you can calculate the voltage generated in that wire by a loop of wire in a changing flux. There's 3 things that can change: the magnetic field, the area, or the angle between the magnetic field and the area. You can see that here. Only one of those will be changing at a time. I will never give you a problem where multiple are changing, because it's going to sound shocking. You need calculus. Look how much you all avoided. So whenever you all hear what's the difference between your all's class and that, there's more you can do with calculus, so you all are spared that discovery. You're spared the excitement. I don't know. View that as a positive or a negative. That's up to you. N is the number of loops. And the other thing that showed up here is if you have, there was a few problems where we had this, where we had a loop that was caused by a rod, kind of that could slide along. And say this rod is sliding to the right. Well, then I'm getting a changing area, which means more field lines. And we get that based on this equation where L is the length of this rod, V is how fast it's going, and B is whatever magnetic field may exist inside that thing and kind of everywhere. But the really interesting thing is you didn't actually need rails for it to slide along. If I just have a moving rod flying through space, the problem is identical, which was kind of interesting. And I explained that was because there's charges in it, they get separated, and therefore you get voltage. At the end of the day, you're going to need to know that voltage equals magnetic field times length of velocity. All of this just calculates the voltage. Does not tell you which way current flows. That's the trend with magnetic fields. I gave you the equation and said, great, we can calculate how much, which way. Introducing the right-hand rule. So, make certain you can calculate this. There was a couple of problems in the last test. Look at those. If you're stumped, look in the problem sets. How do you find the direction of current when this is happening? You follow these steps. What is the direction of the existing magnetic field? Whatever is happening, am I getting more or less of those? Whatever is happening, I want to counteract it. If I'm getting more of them, make a magnetic field the other way. If I'm getting less of them, make a magnetic field the same way. Counteract the change. And then we used right-hand rule 2.5, which was, if you have a loop, put your thumb in the direction of the magnetic field you want, your fingers will tell you the current that'll make that. If you have a loop, put your finger in the direction of current, that'll tell you the direction of the magnetic field it makes. Kind of a simplification. So, real quick, if I have a loop that is entering a magnetic field that is like this, that is into the page, so it starts there, at some point later, bam. Oh no, my flux changed. I'm getting more field lines into the page. What is it going to do to counteract that? It is going to make field lines pointed out of the page. It wants to counteract the change. If it's getting more, it wants to make some the other way. If it's getting less, it wants to make more. So I'm going to make a magnetic field that is out of the page. Right-hand rule 2.5. Thumb is in that way. Bam. Counterclockwise current. Please review these ones because I know this is two concepts and one problem. So this is going to make a current counterclockwise to make that field. You do right-hand rule 2.5 as the last step. Find what field you need to counter the change, then use right-hand rule 2.5. It's the very last step. Most of the challenges I saw students having was doing the opposite. Or not doing the opposite, but trying to use right-hand rule 2.5 almost immediately. Use it at the very end. So, if I have this exact same problem, not the exact same problem, if I have a loop, and instead of it entering the field, it's now exiting the field, so it's basically the same problem, but as it leaves it, oh no, I'm getting less field lines. Don't like that. I want to counteract the change, and this will make a current. You can do the right-hand rule to prove for yourself that this will make a current clockwise. Okay. All right. Awesome. That is all magnetic field stuff. Last little bit is what we spent the last 2 weeks doing, which should be the most fresh in your mind. So we have 10 minutes, should be able to knock it out. Timing worked out pretty well, actually. I didn't know how this would go. This was everything on test 2. Series and parallel circuits and magnetic fields. A whole bunch of magnetic fields and a whole lot of waving your hand around. So we talked about electric fields, charges, electric fields, force, do that. We talked about moving charges experiencing magnetic force. And then we said, well, something interesting. We've been talking about charges and circuits and all these things, and then we kind of jump to something that seems completely different than it all. We jump to light, and we say, oh, guess what? Light is an electric field and a magnetic field, which seems like a really big jump. Now, we've been talking about these things, and then how the heck does light relate to it? Light has no charge. There is no charge associated with light. It actually has no mass. It's not really made of any. It's just pure. It's just energy. But turns out that it is an electric field or magnetic field. Light isn't just what you see with your eyeballs. Radio waves, X-rays, gamma rays, great. All of it travels. This was a question on the quiz. I just posted the solutions to the last quiz, so if you're curious on any of those, feel free to check it out. One of the questions I know that threw people for a loop was I said, hey, here's two waves, two different frequencies. How do their speeds compare in vacuum? It's the same. All light in vacuum travels at the same speed. Visible light, X-rays, infrared, gamma rays, ultraviolet, blah, blah, blah. All of them travel at 3 times 10 to the 8. That is the speed limit of the universe. You cannot go faster. You can certainly go slower, but you cannot go faster as far as we currently understand. Super simple relationship between the electric field, magnetic field, and the speed of light. C equals EV, E divided by B. We introduced something called wavelength and frequency. So you have a wave. Frequency is how often you see it pass you by. Wavelength is the distance between 2 points. And we found they're inversely proportional. The more squished it is, so that's maybe a low frequency, and this is a high frequency. So low F, high frequency. But the wavelength went down. Super easy relation, super nice relationship. C equals F times lambda. The energy of a wave is purely dependent upon its frequency. Energy equals h times f. H is a constant, which I will give you. It's called Planck's constant. Comes up a heck of a lot when we talk about small things. If your brain is feeling like this is a lot of information, you're in good company. I'm also tired from talking. This is a lot. This is the entire course in 80 minutes. I know it's been a whole monologue of me just going really fast, but it's the whole course in 80 minutes. Feel free to please look back at this and just kind of check the sections that you were the most uncertain on and that you maybe performed the worst in, and those are the best ones to review. Electromagnetic waves, light hits. I've just got a couple more. Light reflects at the same angle it hits with. If it comes in at 30, it bounces off with 30. Light acts like a bouncy ball. If it comes in with 30, it bounces off with 30. Great. Light travels slower in denser materials. I told you all that light travels at the same speed everywhere. Feel free to look up why both of these things are true. N equals C over V. N is the index of refraction. N is greater than 1 always, because by definition, if C is the speed limit, V has to be smaller than it. Otherwise, you get a number. If you ever find a material with N less than 1, you have found a material where light travels faster than the speed of light. Go win your Nobel Prize, move on with your life. But, yeah, I don't think it's going to happen. I don't know. Maybe it'll happen. Probably not. Higher N means more dense material. That's higher, more dense material, and light travels slower in that material. We got our whole bendy thing going on here. Light bends as it goes from one material to another. Snell's law, N1 sine theta equals N2 sine theta. If N2 is bigger than N1, then I think I actually have this backwards. Then theta 1, Theta 1 should be bigger than theta 2. So it's the opposite of what you'd expect. When you go from a less dense to a more dense, the material, so let me put this in the order that makes the most sense. When you go from a less dense to a more dense, the angle gets smaller. So I actually had this backwards. If N2 is less than N1, it does the opposite. Theta 2 will be bigger. At which point you can actually get your critical angle. That's the point at which it does not leave. We showed the simulation. There's some problems on that. Really good pictures. But that is light hits, bam. And then it travels at like that 90-degree angle, which basically results in that equation. I'm not going to draw a picture for it. It'll just make it more confusing. Make sure you can do the problems on the critical angle for sure. This is what fiber optics works with. All right, optics, easy peasy. Magnification, height of image over height of object. Divide how big your image is divided by the object equals the negative distance to image over distance to object. And then you have this super simple equation, P equals 1 over F power. Power, that was the number on your contacts, if you wear contacts box. negative or positive. Positive, F for convergent lens, negative for divergent lens. But these are kind of two equations in one. Power equals this, or 1 over F equals that, and power equals that. A equals B and B equals C. Go through the problems. You're probably currently doing that anyway. But this equation is fairly straightforward. The only thing that you need to be careful of, is this right here. F is positive for convergent lenses and negative for divergent lenses. Keep harping on that. So if I tell you in a problem, I have a divergent lens with a focal distance of 3 centimeters. You need to convert that 3 centimeters to a negative. You need to chuck a negative sign in front of it. I will not put that negative sign in front for you because I want you to remember that that is the difference between these two. And then all the math will end up getting you DI, positive or negative. That does matter. And then after this, the next slide is just showing a picture of which way the light rays go. My best recommendation to you, just have that picture on a note card. Have a picture of what the light rays look like due to a convergent lens and a divergent lens. You could draw it yourself. You could print it and glue it to the paper. Pick your poison. Here's a picture of it. It's one for my slides. There's lots of ones online. Find the one you like. Convergent lens, light rays converge, make a real image. Divergent rays, they diverge. And that's our whole class, y'all. That was a lot. Probably wasn't very enjoyable, but it was everything we learned in 80 minutes. And you can go back. This PowerPoint hopefully will be a good resource for you all to kind of overview and just be like, hey, this is what I learned in this class. May not have liked it, but hopefully you learned it. So kind of satisfying that everything can fit in 21 slides. There's a heck of a lot of work in between for sure for you all. I know that. So good work, y'all. Thursday will be the number crunching. Do some problems. Again, no clicker questions. I may ask clicker questions, but they won't be worth any points. So like I may still have opportunities for you all to engage. Hopefully it'll be less mentally exhausting than today. We'll see. But please, look through this when you're studying. Stop at places that you don't remember. Stop at places that you are confused about. And do problems in that area. If you understand the concepts, you will be able to do the problems more confidently. There is a reason for understanding this.
Thank you.
Yeah, have a good one. If y'all have any questions, come on up. But enjoy the time. Yeah.
3 note cards for these files?
Either 3 note cards or 1 sheet of paper front and back plus a note card front and back. Comes out to the same. Yep.
And 40 questions multiple choice.
And 40 questions multiple choice. No free response because I don't want to grade free responses. But that's basically what it comes down to. I've got a short period of time and don't want to grade as much. So 40 multiple choice. The curve, if there is a curve, it'll be the exact same logic. If the average is less than 75, I'll add points to get to 75. So all the grading will remain consistent.